Good afternoon, ladies and gentlemen. Thank you for taking this time to view our presentation for the 2021 RASC-AL competition. After months of research and collaboration with our advisors and many supporting actors from across the country, the United States Naval Academy is honored to present our design concept for the Theme 3 Venus Flyby. Our team has dubbed this design as the Venus Interplanetary Researcher and Testbed for Uncharted Exploration, or VIRTU for short. Our team is composed of 11 aerospace astrotrack engineering undergraduates from the class of 2021. To complete this research, every member was designated a subsystem to become the engineering specialist for. Our presentation will introduce our engineering approach along with the overview and primary impacts of the mission. Following this, we will introduce our concept of operations and cost analysis. The presentation will then go through the subsequent subsystems by their engineers and will conclude with the overall risk assessment before Q&A. To reiterate our mission, the mission of the VIRTU project is to send a spacecraft manned by 4 astronauts on a trajectory that will pass by Venus and deploy a probe into the Venetian atmosphere. The spacecraft will take advantage of its proximity to the planet to conduct low-latency data collection and analysis before returning safely to Earth by December 31st, 2034. The mission will use the extended time in the deep space environment to study the effects of a long-duration mission on a human crew. Design and construction of the entire project will not exceed an annual budget of $2 billion per year beginning in 2025. Following this, we took this and produced 4 primary mission objectives to flow down from while designing the system and subsystem requirements. On this next slide, we have just one example shown of this flow down process. These requirements serve as our reference guide for the entirety of the design process. Our overview chart displays the primary innovations that we'll be covering during this presentation. The primary innovations include interplanetary space habitat system, nuclear thermal propulsion system, low enrichment nuclear fuel sourcing, optimized interplanetary travel, a multi-launch system, Venetian atmospheric analysis probe, stuffed Whipple shield design concept, LDHEO model stationing, interplanetary orbit-induced coma experiments, amongst others, and these will be discussed in further detail later in the presentation. Assessing the overall impact of VIRTU and its use to NASA, we looked at the societal and environmental impacts. VIRTU will ensure that NASA guidelines are followed throughout all launches and operations. We have also addressed that our concept for the propulsion system presents a potential risk of radiation exposure to the nearby area. In regards to Venus, the probe will be the only man-made item to enter the atmosphere. To mitigate contamination to the Venetian atmosphere, the probe will be decontaminated per NASA guidelines. We have also designed our flight path and mission operations so as to prevent contamination due to waste from the spacecraft other than the probe. Overall, our goal is to increase support from the public, industry, and Congress that manned interplanetary travel can not only be feasible, but cost-efficient and repeatable. We plan to have the success of VIRTU to be a stepping stone towards Mars exploration by providing a successful demonstration of innovative technologies that could be applied to those future missions.
The VIRTU spacecraft assembly is composed of 2 crew-accessible modules towards the bow, a living habitation in an onboard laboratory, 6 fuel tank modules amidships, as well as an engine module supporting 3 HALEU nuclear engines toward the stern. The crew-accessible spaces are in line with the 2 largest fuel tanks in the engines. The 2 smaller fuel tanks on either side that are not in line with the main VIRTU assembly will be dropped over the course of mission burns to reduce the mass of VIRTU as it hurtles towards Venus. A capture system compatible with the NASA docking system, or NDS, is positioned on one side of the onboard laboratory. A payload compartment housing the Venus probe is positioned on the other side. A series of radiator panels will also deploy from VIRTU when the spacecraft is completely assembled. The VIRTU modules will be launched into orbit on board 6 SpaceX Super Heavy launch vehicles with extended fairings. The first launch will deploy the main engine module with the 3 HALEU nuclear engines. Fuel tanks will then be launched in the 4 subsequent vehicles and guided one by one to the engine module using the Storm docking and navigation system in tandem with 8 Aerojet Rocketdyne hydrazine thrusters that are affixed to each VIRTU module. Once the fuel tanks have been mated using a large docking rig based on NASA's hard capture system, the crew-accessible spaces will be launched together in preparation for receiving crew members through the docking port.
Once VIRTU has been constructed, it will autonomously conduct its 2 orbit-raising maneuvers. The first burn puts VIRTU into an elliptical orbit, where the spacecraft will discard the first and larger set of drop tanks. The second burn will place VIRTU into a lunar distance high Earth orbit, LDHEO, and the second set of drop tanks will be discarded. Once in LDHEO, the crew and supplies will be launched on board an SLS Block 1 and Orion spacecraft. The crew will rendezvous, transfer to VIRTU, and prepare for Earth departure. VIRTU will then burn to begin its 125-day transit to Venus. During this transit, mid-course corrections will be needed to stay on course and finalize the flyby trajectory. Transit time will be utilized for experimentation and to conduct a study on the effects of long-duration deep space flight. When Virtue is 1,100,000 kilometers from Venus, the probe will separate from Virtue and begin its mission while Virtue continues on its set path. At the periapsis, Virtue passes Venus at 10,000 kilometers above the sunlit side in order to accelerate and adjust Virtue's orbital inclination to help create a favorable return trajectory. After departing Venus's sphere of influence, Virtue will conduct its trans-Earth insertion burn to raise the apoapsis of its solar orbit in order to increase dwell time and allow for Earth to catch up to Virtue. Similar to the transit to Venus, the return transit to Earth will require multiple maneuvers, and deep space flight experimentation will continue. Upon Virtue's return to Earth, it will burn to enter back into LDHEO. From here, another Orion spacecraft will launch aboard an SLS Block 1 to return the crew to Earth. Virtue will then remain in LDHEO in order to be serviced, refueled, and prepared for future use. The LDHEO orbit requires less than 100 meters per second delta V to enter a near rectilinear halo orbit, NRHO, around the Moon, where the Lunar Gateway will be stationed, allowing for manned maintenance and refueling from future Moon-based liquid hydrogen production. Utilizing this mission architecture allows Virtue to be repurposed and modified for any future missions, fitting into NASA's current plans for manned mission to Mars. These orbital diagrams show the track Virtue will take as it departs Earth, travels through interplanetary space, and returns to Earth. The raising burns are shown in white on the diagram on the left, and the white represents the outbound track on the diagram on the right. Purple then represents the return trajectory in both diagrams, and specifically the final orbit of Virtue in the diagram on the left.
This diagram displays an overview of Virtue's flyby of Venus. Virtue will deploy the probe 1.1 million kilometers away from Venus, and with the addition of a burn using its hypergolic thrusters, the probe will reach Venus 105 minutes prior to Virtue entering communication range. The probe will then remain in contact with Virtue for the next 124 hours. This image shows the concept of operations for the probe's deployment within Venus's atmosphere. The probe will use aerobraking, a hypersonic inflatable aerodynamic decelerator, or HIAD, and a parachute to slow the descent before deploying the balloon, which keeps it aloft at 60 kilometers altitude. Each piece of speed reduction equipment used to slow the probe was chosen based on limiting factors such as the Mach number needed to deploy different equipment or the altitude where the equipment needed to be deployed.
In order to determine the initial estimates for the cost of the Virtue mission, we utilized NASA cost model guidelines created from data collected during the 2010 fiscal year. Taking into account estimated costs for materials, facilities, and launches, we have a rough assumption of $17.72 billion after inflation for overall mission costs, with pay distribution shown in the chart in order to make payments. The 10% section in the red of the chart serves as a visual demonstration that the annual budget does not exceed $2 billion even after applying the margin. Overall, we initially had a goal of 15 to 20% of margin for the cost, but estimates have set out at 11.3% for the overall duration of the mission. This is primarily due to the high research and development costs expected due to many of the technologies, the nuclear thermal propulsion, and human space habitat systems as the primary costs.
The A modules that make up the Virtue assembly, previously shown assembled in slide 10, has 4 crew members and each subsystem is necessary for our mission to Venus. Mass budget allocations for each subsystem, specified on the right-hand side of your screen, are based on estimates from each of the Virtue subsystem leads. These estimations lead to our decision to employ 6 SpaceX Super Heavy launch vehicles in order to get Virtue into orbit. The Stage 1 and Stage 2 fuel tanks that will be mated and affixed to either side of the Virtue inline module assembly hold a cumulative 1,390 cubic meters of hydrogen. The Stage 3 bow and aft inline fuel tanks, which will not be dropped until the end of Virtue's mission, contain 1,430 cubic meters of hydrogen. The onboard laboratory and living habitation, which make up the bow of Virtue, contain nearly 580 cubic meters of crew accessible spaces. The total length of the Virtue assembly will be 59 meters. Virtue's crew accessible spaces will be enclosed by a multi-layer Whipple shield to protect against radiation and MMOD, as well as provide thermal control for inhabited areas. The outermost layer, a bumper, acts as a small MMOD shield. MLI insulation, analogous to the current MLI used on board the International Space Station, will make up the second layer. Intermediate layers of fiberglass and polyethylene will then be placed to mitigate radiation, with the final aluminum rear wall acting as the innermost layer for these spaces.
Thermal protection for Virtue has been inspired by heritage designs that have proven their use through multiple different missions around Earth and to Venus. For insulation, Mylar and Kapton will be utilized as the form of multi-layer insulation. Water loop system utilizing ammonia that comes from the water supply of the spacecraft, as well as the heat rejection system radiators that are used on the ISS, will regulate heat across and away from Virtue. We are expecting an exceptional amount of exhaust heat from the reactors, so we have constructed a heat piping design that utilizes 8 assemblies that can attach anywhere from 4 to 8 panels in each assembly. A heat piping system will also send the heat along the spacecraft to the radiators to efficiently expel heat away and to help regulate the temperature on both sides of the spacecraft. The success of these designs in the past allows for Virtue to have a historically reliable thermal control system.
The interior layout of Virtue can be seen here. The total habitable volume comes out to be 322 cubic meters, of which 130 are allotted for the laboratory and 192 are for the habitat. We've also constructed a 3D cutaway model to help convey the layout. Virtue provides a fully closed, partially regenerative, environmental control life support system to maintain the health and well-being of our 4 crew members. One of the biggest challenges to this was increasing water reclamation rates for existing ECLS systems. With the use of the exploratory water recovery system that has a standalone recycling rate of 94.5%, in conjunction with a new state-of-the-art brine processing assembly that works in tandem with the UPA and UTS, Virtue can provide a 98% water reclamation rate. The daily caloric intake per crew member is set at 2,250 calories. 40% of the food offered will be dehydrated products, 40% will be thermostabilized packaged items, and 20% will be commercial off-the-shelf products. We have estimated that 3,742.3 kilograms of food will be sufficient for the mission. The crew will also continue NASA's efforts in hydroponics by testing pick and eat capabilities of the 6 onboard veggie systems, allowing them periodic access to fresh produce during the mission. The oxygen generation system on board is the same as the current flight-tested and operational OGA on the ISS, but with listed changes to limit crew maintenance and increase reliability, expected to be completed by 2024. The crew will not be receiving full-body radiation gear due to the duration of the mission. Instead, we are using a layered approach, using the stuffed Whipple shields placed strategically based on crew schedule, the uniform thickness of the crew module, and lining the ORUs around the perimeter of the module. The crew will also receive the AstroRad and STEM-Rad Gamma 360 harness and vest. Expected levels without the use of gear are expected to be 10.602 rad per crew member for mission duration. Within the lab module, Virtue provides an exercise facility for crew members equipped with a Colbert treadmill, resistive overload combined with kinetic yo-yo, which is a low-mass arid alternative with an erg configuration if needed, and a bicycle. The crew is mandated to exercise 2 hours a day, and fitness evaluations are also factored into the crew's day to monitor and measure degradation in the musculoskeletal system and motor skills. The crew receives a minimum of 8.5 hours of sleep daily, with the option to forgo personal time for more sleep. The psychological health of the crew is primarily maintained by offering 30-minute video calls to friends and families daily, which helps combat social isolation and homesickness. Listed are the multitude of other outlets Virtue will provide to limit stress overload for the crew.
The criteria in determining the propulsion system Virtue should use was founded in 3 distinct manners. No human-rated spacecraft has ever ventured further than the Earth-Moon system. The total mission duration is a relatively short 13 months, and it is extremely massive. For size comparison, Cassini-Huygens was the most massive deep space probe ever launched by NASA, and it is only 1/70th the wet mass of Virtue. When considering these constraints, the feasibility of the large array of propulsion systems narrows down greatly to a select few. Some requirements for Virtue include high delta-V capabilities, reliable, restartable, relatively low mass, relatively high TRL. In addition, high total impulse would be beneficial, high thrust, and an innovative propulsion system. On the screen now is the simplified version of the team's trade study conducted to determine the most appropriate propulsion system for the Virtue mission. Bottom line decision was, although there were several options available, key performance constraints such as excess burn time, initial mass, and low technology readiness levels led to nuclear thermal propulsion to be the decisive choice for Virtue. Nuclear thermal propulsion, also known as NTP, works by using a nuclear reactor to heat a propellant to extremely high temperatures before ejecting hot exhaust through a nozzle, producing thrust. NTP was considered for this mission due to several advantages it poses. Depending on the system selected, it can provide relatively high thrust, high total and specific impulse, high delta V, which are essential to reduce the duration of the mission. In addition, it is restartable and has a relatively high technology readiness level of 6, with extensive progress and efforts being made in recent years. So although NTP may not have been the best choice in each individual metric of performance, such as engine mass and operating time, it was the decisive choice with all the metrics combined as the best performance overall. This propulsion system will comprise of 3 high-assay, low-enriched uranium, or HALEU, nuclear thermal rocket engines that provide a total of 333,000 newtons of thrust, a specific impulse of 900 seconds, and a total mass of 15,000 kilograms. 3 engines will be used to maximize the total impulse, provide enough power to the rest of the spacecraft subsystem, and as insurance in case of an engine failure. The propellant that will be passed through the reactors will be liquid hydrogen, commonly shortened to LH2. The decision for LH2 as the propellant is due to its extremely low molecular mass, which directly increases the exhaust velocity and therefore overall performance of the rocket, as well as its low cost and relative ease of production for rocketry and repertoire as a successful propellant in tests. 210,000 kilograms of LH2 will be needed as a propellant as well as coolant for the reactor during operations via regenerative cooling. To contain the LH2, 6 cryogenic tanks will be utilized, resulting in approximately 47,000 kilograms worth of inert tank mass. When combined with the dry mass of Virtue after full assembly in low Earth orbit, approximately 77% of mass will come from the mass of the propulsion system itself. To greatly reduce or eliminate liquid hydrogen boil-off, several trade studies are being conducted in the industry with the anticipated cryogenic fluid management, or CFM, system to be Carrier LLC's 20 Kelvin, 20 watt cryocooler, which is still in development. There are several risks associated with using NTP, the most important of which we will discuss later in the presentation. Our propulsion system will also be responsible for the spacecraft's power generation, which will be covered in further detail by our power subsystem lead, Jim Gale.
Virtue's power budget was defined by the end-of-life peak power requirements of all subsystems operating simultaneously. The table on the right side of the slide displays each subsystem's requirements, totaling to 24.32 kilowatts of electrical power required. These power needs are met by 3 bimodal nuclear reactors. These reactors will produce 25 kilowatts of electrical power while operating at just 33% of their design power mode capabilities. As previously stated, the reactors will operate in 2 distinct modes. In propulsion mode, electrical power is generated through the expander cycle, as seen on the left side of the figure shown. When propulsion is not necessary, the reactors will operate in a passive power mode. In power mode, heat generated by the reactor cores are transferred to 3 closed-loop Brayton cycles. The closed-loop Brayton cycles, shown on the right side of the figure, utilize a helium-xenon mixture as the working fluid and are expected to produce between 7 to 25 kilowatts of electrical power each, depending on the reactor power. 2 designs were considered when selecting the nuclear thermal reactor, the Triton and the Canooter. Based on the Virtue power requirement of 25 kilowatts of electrical power, the Triton was able to meet the requirements while operating at a lower power and producing significantly less waste heat. Since the Virtue spacecraft's main constraint is heat dissipation, the higher mass Triton system proved more desirable than the more compact Canooter design.
The 4 major components of the guidance, navigation, and control subsystem are attitude determination, relative location determination, momentum storing and dumping, and docking. Attitude determination will be done using inertial measurement units that are composed of fiber optic gyros and accelerometers. Star trackers will provide increased attitude accuracy while supporting location determination. 4 double gimbal control moment gyros will store secular momentum until they are saturated. This provides an electrically powered alternative to using only fuel-powered thrusters for course corrections. Docking will be done using an autonomous rendezvous and docking sensor suite that includes a flash LiDAR vision navigation sensor, a visible camera, and long-wave infrared cameras. The benefits of using this suite of sensors comes from their compact designs, their increased performance in dynamic docking situations compared to slower processing scanning LiDAR systems, and their adaptability to different space lighting conditions.
Virtue is equipped with 8 radial line slot array, or RLSA, antennas, 6 of which are located on Virtue itself, while the other 2 are located on the probe. Because each RLSA can operate only in one designated frequency, each link requires 2 antennas, one for transmission and one for reception. Parameters for each antenna are found in this table on the right. All frequencies are Deep Space Network compatible, and Virtue will communicate directly with the DSN via line-of-sight links. RLSA antennas were preferred over parabolic antennas due to their resistance to thermal damage and interference. They are significantly smaller and lighter than parabolic antennas, allowing for more of the spacecraft's mass to be allocated for larger subsystems. The sole disadvantage of RLSA antennas is the fact that they cannot be readily pointed toward a ground station without moving the entire spacecraft. However, a simple solution to this problem is to mount each antenna to Virtue using 3 telescoping arms on sliding tracks, as shown in these images. By controlling the angle and length to which each arm extends, the antennas can be accurately pointed toward Earth, regardless of Virtue's orientation in space.
The command and data handling system can be seen here. There is a real-time processing software for vital subsystems that need to be monitored at high accuracy, and automated software for daily taskings for the onboard computer. Virtue's onboard computer is the RASC-750. The software and hardware for the command and data handling system contain components from the Missile Defense Agency, as well as Johns Hopkins Applied Physics Laboratory. The most significant component is a solid-state recorder storage system design. 30 solid-state recorders will be utilized for data storage. One has the storage capacity of 512 gigabits. This storage system will cover 1.92 terabytes of data for the entire mission while providing a high percentage margin risk.
The probe design was designed to be attached to Virtue without taking up too much mass, and as such will have a mass of 150 kilograms and will be about 2.5 cubic meters in volume. The probe will travel a downrange distance of 2,700 kilometers while descending through Venus's atmosphere and using its various means of technology to reduce its velocity. Upon slowing from its entry velocity of 11 kilometers per second to 50 meters per second, the probe will use a balloon to stay around 60 kilometers above the surface and will use various equipment to search for evidence of phosphine in the atmosphere, as well as to record other atmospheric data. This recorded data could lead to a better understanding of Venus and would provide valuable information needed for future Venus missions. Venus, where Virtue will carry 2 experimental payloads, with the first being an experiment involving induced hibernation in mice. The experiment would use chemicals to induce hibernation in 10 mice while using 10 separate mice as a control group. These mice will be kept in 5 rodent habitat hardware systems as seen in the image. Induced hibernation in non-hibernating mammals could provide benefits for the future of extended human spaceflight in areas such as reducing food and water intake, as well as reducing radiation effects from the deep space environment. The second scientific experiment consists of testing the effects of antimicrobial clothing in an effort to reduce the mass of clothing required on a long-duration space mission. Currently, clothing is disposed of when it gets dirty in space, with no way of cleaning it. Antimicrobial clothing would theoretically last much longer before it must be disposed of. Virtue will carry ordinary astronaut clothes as well as antimicrobial clothes and record the observations and results of both types of clothing.
Lastly, the risks associated with the mission were categorized using the NASA Risk Assessment Matrix. Individual subsystem engineers determined potential mission and safety risks due to operations, designs, and constraints. A few of these examples are shown here to include the risk of solar particle events, the death escaping contamination from the lab experiments, failure of computer systems to either capture data from the probe or send back data to Earth, and a few others. Along with these, mitigation options have also been determined to reduce the likelihood of these events occurring during the mission. Regarding concerns for the reactor, redundant detectors and shutdown procedures will be implemented. The risk of radiation exposure to the crew is fairly low in comparison to the risks from solar radiation and galactic cosmic rays. The radiation protection systems, as stated previously, are sufficient in ensuring the safety of the crew. In a worst-case scenario that the mission may need to be aborted in flight early life, it has been determined that early home course corrections can be made if it is believed that the full mission cannot be completed. The success of the Virtue mission is critical. However, the safety of the astronauts has and always will be the first priority. The risk assessments are ongoing, and our systems engineering approach allows the project to stay flexible in order to ensure safe success of the mission. Once again, thank you, ladies and gentlemen, for hearing our presentation for the RASC-AL competition. We will now take this opportunity to answer any questions that the viewers may have.